Electrons and energy levels. So electrons cannot be located exactly, but we know that they exist in energy levels. And sometimes we call these energy levels shells. So sometimes these are referred to as shells or electron shells. But these actually form the electron cloud, but each in the cloud you have different levels of electrons. So most of the atom is empty space. So the nucleus is actually, this is not to scale at all. The nucleus is about 10,000 or 100,000 times smaller than the electron cloud. It's like putting a marble in the center of a football stadium. The football stadium itself would be the electron cloud. The marble would be the nucleus. So most of the atom is really empty space with these electrons flying around. So the size of the atom then is determined by the electrons in the electron cloud. It's also these outside electrons or valence electrons that tend to interact with everything. So they interact with other electrons and repel things. They also interact with other valence electrons and have chemical reactions occur, bonding, etc. But energy levels hold limited numbers of electrons. So they go in orders of 2, 8, then 18, then 32, etc. And actually the formula for this is 2n squared. So n squared is the level squared. So if you're on the second level, for example, it'd be 2 squared. So 2 squared is equal to 4. Okay. Then take 4 times 2, and that equals 8. So the number of electrons that can go in any level is going to be 2n squared. The maximum number of levels is 7. Now, for all practical purposes, we never really get above 32 electrons in any level, even though higher levels can hold way more electrons. So some examples over here. We have hydrogen. Basically, to show the electrons, you have one shell, you got one electron. Oxygen, you have two shells. You got a shell here and a shell here, or two energy levels. The first energy level has 2 electrons in it. And then the second energy level has 6. 1, 2, 3, 4, 5, 6. So it's a total of 8 electrons. And 8 electrons with 8 protons gives you a neutral atom. Aluminum, you end up with 3 different energy levels. And it's basically 2 electrons in the first energy level, 8 in the second, and then 3 in the third. So valence electrons, I kind of mentioned this a second ago, but the valence electrons are the outermost electrons. Okay, so the outermost electrons of an atom are called the valence electrons. And these really determine the chemical properties of the element. So the number of valence electrons determines the chemical properties of the element because they're on the outside of the atom. They are what interact with the rest of the world. And then elements with the same number of valence electrons tend to have similar chemical properties. So for example, sodium and potassium. Sodium is Na, potassium is K. Okay, both of these have 1 valence electron. So if I look at the diagram here, my sodium, I have 1 valence electron there. Potassium down here, write this a little bit different. We're just writing it with the 1 valence electron. If you did all the energy levels, potassium would have 3 energy levels, like the full set of energy levels for sodium, plus 1 extra electron in another energy level, so a 4th energy level. So really, you have 4 levels for potassium. But there's still just the 1 valence electron. So they have similar properties. So both of these are highly reactive metals. They both react violently with water. They react with other elements very easily. They combine easily with other elements such as chlorine, which has 7 valence electrons. So chlorine has 7 valence electrons. If we look at the diagram here and kind of count the ones on the outside, here's 2, here's 4, here's 6, and there's 7. We can also write it like this and not worry about the inner electrons. This is a Lewis structure here. So Lewis structure, we just ignore the inner shells of electrons and just really draw the electrons that are in the outer shell, because again, those are the ones that are interacting with the world. But you end up with sodium chloride, so NaCl, and potassium chloride, KCl. So we see in the sodium chloride, basically the one extra electron goes from the sodium to the chlorine. So the chlorine has one extra electron now, so it's a -1 charge. The sodium has lost an electron, so now it's a +1 charge. Potassium chloride does the same thing. This electron would actually come over here to the chlorine, so then you end up with a +1 for your potassium and a -1 for your chlorine, and then you get your compound, your salt. Noble gases. So noble gases are elements with full valence shells. So the outer shell is full. Group 18 on the right side of the periodic table, those are the noble gases. And these are what all the other elements want to look like. All the elements want to look like the noble gases. Okay. The noble gases have 8 valence electrons, and that makes a full shell for most elements. So the noble gases, like argon, naturally have 8 valence electrons, so they don't really react with anything. We call this the octet rule. So the octet rule says that elements will try to gain or lose electrons to look like a noble gas. They want to have 8 valence electrons. So our example here is argon, has 18 total electrons, so you got 2 in the first level. So you got 2 here, plus 8 here, plus another 8 here. So 2 in the first level, 8 in the second level, and then 8 in the third level. So you add those up and you get 18 electrons. Comparison of noble gases to other gases. So oxygen and hydrogen are 2 other gases. These are both very reactive. They will react with other things very easily. They do not have full valence shells. So if we did a Lewis structure for oxygen, it would basically have 6 electrons. Okay. If we did a Lewis structure for hydrogen, it's just 1 valence electron. So these really want full shells. They'll either give up an electron or try to gain an electron or 2. Like oxygen tries to gain 2 electrons. Hydrogen tends to give up its electron. The noble gases, though, are not reactive because they already have full valence shells. So they are not reactive. They don't really react with a lot of things because of that.